Hey there, I'm Nix, and the topic for today's video is solving the linked list cycle problem on the LeetCode website. As always, I'll give you all of the details about the entire process, through the planning of the algorithm, to the coding of it, to the analysis of time and space complexities, as well as looking at the LeetCode rankings. If that sounds interesting to you, then stay tuned. Welcome back. Now, last time we solved the design linked list problem, and unfortunately, the very next thing after that is locked away via premium access, but this is only the solution to this problem, so skip! And we're now on to this problem, linked list cycle. So with that, let's get right to it. We are given the head of a linked list, and we want to determine if the linked list has a cycle in it. There's a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. So basically, around and around we go forever. Now, internally, it gives us some details as to how this is done, but for the purposes of actually solving the problem, this is not relevant, but it is useful for creating custom test cases. Internally, they're using a position variable to denote the index of the node that the tail's next pointer is connected to. And we want to return true if there's a cycle in the linked list, otherwise we want to return false. And then we get some handy-dandy examples here. Example 1, we have 4 nodes, and the tail node loops background and has its next pointer pointing back to the second node in the list here. Down, looking at constraints here, we have a range of the number of nodes that we can get, we have a range of values, and the position is either -1 if there isn't a cycle, or there's a valid index in the linked list. And then finally we have a follow-up question. Can we solve it using big O of 1 space complexity, i.e. constant memory usage? And as this section's name kind of indicates, that can be done with using the two-pointer technique. So we have a list, and we're going to create, aptly, 2 pointers. They're both going to start at the head of the list. One of them is going to take 1 step every loop iteration. The other one is going to take a different number of steps. It can't technically be anything other than 1, but I'm just going to have it as 2. So the slower pointer is going to take 1 step every time. The faster pointer is going to take 2 steps every time. Okay, so how does that help? Well, in that situation where the pointers are like runners on a track, you're eventually going to get into a situation if they're running around on a circular track where the fast runner is eventually going to lap the slow runner, which means eventually you're going to get to a point where the slow runner and the fast runner meet up at the same position again, i.e. both of the pointers are at the same node. And that is our condition that we're looking for to determine there's a cycle in the list. If we don't, there is not, and we can return false. So we create 2 pointers, start them both at the head, and then as long as we haven't reached the end of the linked list, i.e. our next pointer is null, then we continue moving on and advancing our slow and fast pointers. Then we have our if condition that checks to see whether they're pointing at the same node, and if that's the case, then we break out of the loop and return true. If we get through all of this and we are given, say, a list with no cycle in it, we're eventually going to run into a next pointer that is null. So in that case, we break out of the loop and we just return false. So with that plan in our heads, let's move on to the code. Here are the variables that we need, which just consists of 2 pointers. Up here in the comments, we're given the details of the structure that they created for those nodes. And of course, in the parameters of this method, we are being given the head. So let's create 2 new pointers, list node asterisk fast runner, and I set that equal to the head. And of course, another list node pointer that I named slow runner, and I also point that at the head. Next up is to start the loop. And since we don't exactly know how long we're going to go for, this is the perfect use for a while loop. Now the condition that I have here is as long as the fast runner is not equal to null and fast runner next is not equal to null. These two conditions are going to ensure that we never get an out of bounds error and that we can always recognize when we've gotten to the end of a list that doesn't have a cycle in it. And I'll go into more details about this using some custom test cases after we have created the entire code. Within this loop, we want to advance our runners. The slow runner is going to be set to whatever its next pointer is. That's going to advance it 1 step. Fast runner, however, needs to advance 2 steps, which means that we have to advance it to fast runner next, and then that node's next pointer to advance it another step. Now comes the if condition check. We want to figure out, next comes the if condition check. If we ever see a situation where the fast runner has essentially lapped the slow runner, i.e. fast runner and slow runner are pointing at the same node, then we want to return true. Last thing to do is if we get through this while loop and we never get the opportunity to go into this if statement, then we need to return false. That is the complete code, so let's start clicking buttons to see if I've messed anything up and do some custom test cases. So it's finished here. We have the first example given and I get the right answer. Great! Let's do a custom test case and let's say we don't have a cycle in this one and let's see what happens. We should get false. Clicking a button and let's see if that's true. Judging, more judging. Okay, good. And that works out perfectly. Let's look at these conditions a little bit more before I do the full shebang of clicking the blue button. Now, when fast runner is equal to null, you have essentially found the end of the list, and that's what happens in this situation. So scrolling up here for a visual aid, imagine we don't have this cycle present. The last node in the list is going to point to null. So with both fast and slow runner starting at the head, slow runner advances 1, fast runner advances 2, so we're at the 0 marker. The condition is checked. Fast runner, being the one that is going to be faster, is always going to be the one that is going to reach the end of the list first, which is why we're looking at that one instead of slow runner. Now on the next iteration, when we try to advance it 2 times again, well, the next pointer is pointing to a valid node, but the next pointer is now going to be pointing to null, which is going to advance fast pointer to that null designation. And thus, the next time we wrap around, we say, hey, fast runner is equal to null, we're at the end of the list, we break out and return false. But what do you think happens if this second section is not present? Boop. Will this specific problem still have no problems? Let's find out. We run the code and we get green text. Doesn't have any problems because, of course, when we advanced 2 times and then twice again, we run into null. So the second condition never triggers and this specific problem doesn't have any issues. Neither, of course, does the one that actually does have a cycle. It's going to work perfectly fine as well. But what happens if we go back to it not having a cycle and instead of having just 4 nodes here, I add a 5th one? What happens now? Pending, judging, and of course we get an error. The reason that this happens is we've advanced too far. Let me use this as a visual aid and kind of augment it using graphics. So now, instead of this, which hopefully I've eliminated here, we just have a 5th node. Again, there's no cycle in it. So we have slow runner and fast runner both starting at the head. First iteration, same thing, 1 step, 2 step. Now, when we do a second iteration, slow does its 1 step thing. Fast runner advances again 2 steps. 1 step and 2 step. We get to the last node. Now, in the 3rd iteration, look what happens. We're at this new fifth node, and we're trying to advance it 2 steps. Well, the next pointer is going to point to null, since this is the tail. But what does the next pointer point to? Well, the code doesn't really know, and thus that's why it's telling us what you're trying to do is kind of undefined. But we can get around this by having that second condition here. In this situation, with this second condition, looking to see if the fast runner next pointer is also not equal to null, then it will catch this situation. We will be, again, at this new node, and then when we go to do the iteration, we'll look at its next pointer, and we will see, oh, hey, we're at the tail of the list, and its pointer is null. So, no cycle, we're done. Break out of the loop and return false. So with an odd amount of nodes here, we need this second condition check to make sure that we can catch all situations where we are at the end of a list with no cycle in it. So, with that said, when we do this again with this condition in, we should get rid of that error and have just green text again, which we do. With all of that said, let's finally click the blue button and hopefully get more green text, which we do. Last thing to do before we look at the rankings is to analyze the time and space complexity. Space complexity is really easy to analyze. Using a 2-pointer technique like this, we're only carving out some constant memory to create our pointers. We aren't creating any other variable length containers like vectors or sets or maps or queues, whatever. None of those exist, so our memory is indeed big O of 1 usage. For time complexity, it might not be overly obvious, but you do have one while loop here. You're advancing pointers and you're checking an if condition. You're doing all constant work in constant time. So the time complexity of this code is going to be big O of n. It's going to be linear. It's going to depend on the size of the linked list. Now, it's not going to be the exact size of the list. It's going to be some multiple of it. But we don't really care about what that particular multiple constant is. We just care it's on the order of n. It's linear time. Last thing to do is look at the rankings here. Okay, middle of the pack here. Interesting. And we have appeared in this section of the distribution as opposed to further down here, which is probably using some alternate methods of actually using a variable container. Alright, that was how to solve the linked list cycle problem using a 2-pointer technique. I hope you found this video useful. If you did, consider subscribing. And with that, as always, I will wish you happy coding and to have a nice day.